Okay, hi everyone. Welcome to the Data Science Seminar. It's really a great pleasure to introduce Casey Garner, who is a PhD student in the math department. He's doing his PhD under the direction of Professor Shuzhong Zhang and myself, and he's going to talk about cubic-regularized Newton for spectral constraint matrix optimization and its application to fairness.
All right, mic is on, we're good to go. And I have the time, so I don't go over. All right, thank you, Dr. Lehrman, for that introduction. So what I want to present today is some work that we recently sent off at the end of August, right at the beginning of September. And it really is an application of cubic-regularized Newton to solve a broad set of matrix optimization problems. And we do have an application in data science for this idea of fair and robust covariance matrix estimation. So my hope is to have the first half basically set up the model that we're dealing with, how we go about solving it, and the last half be more about the application that we focused on as an example of this broader class of models that we handled. All right, so our main model for consideration today is going to be a smooth matrix optimization model. It's going to be non-convex in nature because we're not going to assume any convexity on the objective function f. We're going to assume that f is at least 2 times continuously differentiable, mapping the set of symmetric matrices to the real numbers. And we have interval constraints on our eigenvalues. So I want my eigenvalues to be all between 1 and 3, or maybe can be equal to 1, but has to be strictly less than 3. And we will assume that these are connected intervals. All right. And this model number 1, does capture a broad class of optimization models that people care about. So one example would be smooth positive definite matrices. So it's very classical to solve a problem over the set of positive definite matrices, semi-definite programming, positive definite programming, conic optimization. These are all instances of this broad class of models. But if you don't want to deal with positive definite or positive semi-definite matrices, the interval constraints we're talking about could say, I just want to lower bound the eigenvalues of my matrix. One benefit with this would be is trying to avoid singularities that might show up. So it's a slight relaxation, say, of the first model, positive definite, or a slight relaxation of positive semi-definite. But you also could say I want bounded eigenvalues. This would be a reasonable thing to do. I don't have an example of a particular model in mind for this, but this is a type of model that would be handled by our general class. Overall, the way I want to break this down is we have the main model, this eigenvalue constrained problem, and I'm going to work on rewriting it as a completely unconstrained model. And we're going to relate those two and see how they're connected and apply cubic-regularized Newton to solve this unconstrained model. And then finally, we're going to look at an application to fairness. So the idea of doing this unconstrained model is I would like to apply higher order methods. And applying on a purely unconstrained model is a much easier task than trying to apply a higher order optimization method on a constrained model. Cubic-regularized Newton is going to be our tool of choice for the moment in this talk to solve the model. The other classes of algorithms are applicable. This is one that we study. And then finally, we'll get to an application, which is always a useful thing to have to motivate your study. So generally speaking, this is what we're aiming for, is to take our first constrained model and rewrite it as this completely unconstrained model. In order to do that, I've added this function g. Now, g is what we're going to be calling a matrix function. It takes a set of symmetric matrices to the set of symmetric matrices, and I'm going to make the assumption that I can write to, and both g and my composition, f composed with g, are going to be 2 times continuously differentiable. The idea being is I want to apply higher order methods. I need to maintain differentiability to do this. So we're going to work to rewrite our first model in the form of number 2 to be completely unconstrained. And then we're going to apply cubic-regularized Newton for this matrix optimization problem. Now, why would I want to write an unconstrained model? Why would I instead just tackle the problem immediately as a constrained problem? Why go through this extra step of writing an unconstrained model? Well, first off, I want to apply higher order methods. Higher order methods have a few perks. One is you often are able to get faster rates of convergence. But more importantly, you can ensure second order stationality for the point that you're returning. In lots of different data science models, if you find a second order stationary point, and I'll define that in a few more slides, if you can find a second order stationary point, oftentimes you can prove in certain cases that are of interest that a second order stationary point is enough to be globally optimal. So an algorithm that returns you a second order stationary point is better than one that returns you a first order stationary point for many reasons, but sometimes it's enough to guarantee global optimality in a non-convex setting, which generally speaking, you cannot guarantee. Secondly, I want to work towards an unconstrained model because if I want to apply a pure higher order method, very often you can't do that directly on a constrained model. You often need to do extra things to protect your algorithm. An example would be if I have a constrained model and let's just apply pure Newton. The Newton direction could very well make me leave the feasible region if I just take a Newton step and I take a complete Newton step. So you have to do different things to protect you becoming infeasible as your iterates progress. And you can protect that in various ways. But if I have an unconstrained model, I don't have to worry about such things. So the class of algorithms that you have at your disposal is much broader. Now, two ways, classical ways that people might deal with a constraint problem is either through, say, barrier functions or, say, penalty functions. And we don't want to use either of these. This is why we go for the unconstrained case. But classically speaking, a penalty function is one that says, I'm going to allow my penalty function P to be 0 if I'm inside my constraint set, and it's going to be positive as I leave. A barrier function is going to be positive always, but it's going to go to positive infinity as I approach the boundary. So if I apply a penalty or a barrier approach, I have this parameter mu in that second optimization model on the right that I'm going to change. So for a penalty model, I'm going to gradually increase mu. So I'm going to solve a sequence of optimization models. And in the limit, if I solve these as mu goes to infinity, I'm going to have a solution to my constraint problem. For the barrier function, you're going to make mu go to 0 because right now we're penalizing it if you go to the barrier. So it's an infinite penalty if you go to the boundary of your constraint set. So I'm going to solve a sequence of models as mu is going to 0. So I'm making the penalty not as bad, or the rate at which it's going to positive infinity at the boundary is going to be less. In both cases, you can prove that if you solve a sequence of these models, you'll get a solution to the original constraint problem. But if I can write it as an unconstrained problem, then I can just deal with the problem on the right. I have a new function f tilde, but now I'm not over the constraint set C. I'm now over the entire vector space that I'm optimizing over. Okay, and this is what we're trying to do here. And in order to do that for our problem, we're going to introduce something called matrix functions. There's various different types of matrix functions, but we'll focus on a very specific instance of it for today. So the idea of a matrix function is I give you a function that takes the reals to the reals, and I'm going to define a matrix function, which takes a matrix and maps to a matrix via the scalar function. So in the case of symmetric matrices, I can do this through the spectral decomposition. So you give me your function that you care to use that maps the reals to the reals, and I'm going to operate on the eigenvalues in the spectral decomposition. So my matrix function is going to take X, I perform my spectral decomposition, and then I'm going to apply my scalar map, which this should be a capital F right here, not a lowercase f, to the individual eigenvalues. Now, one question that a set of mathematicians should ask is this well defined? I have lots of choices for a spectral decomposition for my matrix, and you can prove that the value of f of x, the value of my matrix function, is completely independent of how you choose the spectral decomposition. This is a simplified version. You can be much more broad, encompassing. You don't need to just deal with the set of symmetric matrices. We can deal with any complex diagonalizable matrix. And there's various types of matrix functions, and we're only dealing with this very specific instance of it. So Hadamard matrix functions, for example, is you could define a single function, scalar function, for every entry of your matrix. You could do that if you want. So by using these matrix functions, though, we're going to encode the constraint set that we have for our original problem. And to see this, we can see this through an example. So if I give you the scalar function x squared plus 3, and I apply the definition of our matrix function, I have my spectral decomposition of x, I have my definition, and now I'm going to apply my scalar function on the individual eigenvalues of my matrix. If we want to rewrite it, we can collapse it down, so that does look like take the matrix x, square it, add 3 times the identity. But the point of this example is that by construction of our function, the matrix that is being outputted by our matrix function has to have eigenvalues strictly greater than or equal to 3. And this is purely based on the scalar function that we have. So I can use this to rewrite our constrained model as a completely unconstrained model. And this is where we get a result. So if I have my first optimization problem, which is our constrained problem, assuming that the set of minimizers for our unconstrained problem actually exist, then I can rewrite different types of interval constraints for the constrained model and have a completely unconstrained problem. And I'm able to obtain the global minimizer to the original problem from the unconstrained problem. So an example would be is this first one. So I want all my eigenvalues to be strictly greater than alpha. And this can be handled by the matrix exponential. And we're adding plus alpha times the identity. And in this case, it's very nice because the matrix exponential is invertible, it's bijective. So you can kind of see the relationship between these two problems. The point is that these functions G are going to map surjectively onto the constraint set. You might grab more things than needed, but it's going to map surjectively. So all possible values of this function are going to equal all possible values that this function can take on in the constraint set. And then we can handle various types of interval constraints. This one is an example where I'm using the scalar definition of G, and I'm not just writing the full matrix expression of the function, because this is an instance where writing the closed form, like I might have in G6, is harder to do here, maybe not possible. So the proof is rather simple. Assuming that the argument sets for the unconstrained models aren't empty, so you don't have the case where the infimum of our unconstrained problem is equal to the minimum of the constrained problem, then all you're really asking in order to prove this is that these maps GK are smooth and surjective. And by previous results, we're able to see that no, the way these functions are defined, they are going to be smooth because the scalar functions that generate them are sufficiently smooth. And if we work through the calculations, we can see that once the scalar functions map onto, that is what the eigenvalues of the matrix are going to map onto. And this is how we can get surjectivity. So the main idea behind this theorem is that these two optimization problems are going to have the same global minimizers. Assuming what I write on the left is well defined. If there isn't a global minimizer to what's on the left, then this equality doesn't make sense, of course. But as long as the global minimizer exists on the left, these two are going to be the same, and we can obtain solutions or approximated solutions to our constrained problem. And it's a non-convex problem, so the best thing you could really ask for is a first order, second order stationary point. Most of the time, a global optimizer for the constrained problem is not going to be possible. But there's a difference here. As I do this, I am changing the landscape of the function that I'm dealing with, so this could be possible and complicate the situation a little bit. And we can try to understand that a little bit more. So before I do that, one quick slide of sort of matrix calculus to at least see the notation that I'm going to be using for the rest of the way. So when I say the gradient of a matrix function that maps a matrix to a real number, I'm going to obtain a matrix, and the entries in my matrix are going to be the partial derivatives. So the ith j entry of my gradient of my function f is going to be taking the partial derivative of f with respect to that entry in my variable matrix. And then I can define directional derivatives in a way that you would expect from, say, dealing with functions in Rn, and I can define a Hessian operator in a similar way. And these things all relate nicely together through their directional derivative. So the directional derivative is the inner product of the gradient with the direction I'm taking the directional derivative in. And the last one, the second order directional derivative, that result looks very similar to what you would think of if I had a Hessian matrix from Rn. I'm going to need some chain rule identities. And part of this is that when I actually apply a higher order method, I actually need to be able to calculate these derivatives. Of course, you could approximate them with like finite difference approximations and the like. Sometimes to prove something or to get a more efficient algorithm, having it exactly is what you would prefer. So in these two results here, 4 is a classical result that you can find in lots of places. The second chain rule identity is useful for us for actually calculating the derivatives in our unconstrained problem. And this was one that we actually needed to prove because I actually couldn't find it anywhere in the literature for dealing with G being a matrix function that is being generated by an analytic scalar function. So I'm not going to show the proof. It's a lot of induction and indice chasing. It wouldn't make for an eventful movie to watch or to populate many slides full. But they're useful to be able to help calculate derivatives that we're actually going to implement in our algorithm. And you'll use these in order to prove relationships between the types of stationary points you'll have in the constrained model and in the unconstrained model. So just to pictorially see the sort of relationship between the unconstrained model and the constrained model, we can look at a one-dimensional example. So what I have in red is this function f, it's a parabola, and let's say I'm trying to minimize this function for strictly non-negative values. So when I look at this plot, I see I have a global minimizer around like say 0.5 there, but I also have a local maximum at 0. So if I apply, say, a change of variable to now allow our function to take on all possible values, all I've done is replace x with x squared. So now I can let x be anything, and all the possible values obtained by the function in blue is the same values that are being obtained by the function in red. But what I have done now is I've multiplied the number of global minimizers that I have. For blue, I have 2 now, though the local maximum is in the same place. Okay, so this is what can happen when we apply our matrix functions to write our unconstrained model. Well, we can relate some of these things together. So one thing to note is that the constraint that we're dealing with is actually a convex constraint. All these interval constraints for our eigenvalues are convex. Our objective function is non-convex. So this is what makes it a non-convex model. The constraint set can be convex, but the objective function is not. If you want to have a convex problem, you really need to have both of those things to be true. And it's not too hard to see that these sets, these eigenvalue constrained sets are convex. They can show it in a few lines, and they all come from some classical results. So it's well known that the set of positive semi-definite matrices are convex sets. So, and if I take plus or minus the entries, it's still a convex set. If I shift a convex set, it's still going to be a convex set. So I can shift both of these sets up, say by alpha I. But then I can take their intersection, because the intersection of convex sets is convex. So you can do this for all of the interval constraints that we're dealing with, but we can see that C is a convex set. And the only reason I have this in here is because I want to relate the first order stationary points of our two models in a way. And because I'm dealing with a convex set in the constrained problem, this allows that relationship to be more easily represented. So a classical result would be if x star is a local minimizer for our constrained problem, then this inequality must hold true at x star, which is essentially saying the directional derivative moving into my constraint set must be positive from x star, which implies that if you take this inequality and you expand your function out with the Taylor series, if you go close enough, you'll see a contradiction will arise. If I say, well, x star is not a local minimizer, I mean, there should be some direction. I get a decrease, a contradiction shall arise. But using this inequality, we can show a result like this, which says, let's say I have x tilde. It is in the set of symmetric matrices, and g of x tilde maps to x star. If x star is a local minimum of our constrained problem, then x tilde is going to be a local minimizer for our unconstrained problem. And what this result says is that all the local minimum that exist in our constrained problem, they're going to show up in the unconstrained problem as long as there's a function, a matrix I can plug into my matrix function that gets out that point. So, which essentially says the unconstrained problem is not missing any local minimizers for my unconstrained problem. And given the amount of time I have, I'm not going to show the proof, but we can come back to it. You can fit it in a single slide. So now we have our unconstrained problem. The global minimizers are going to be the same. I know when I write the unconstrained problem, I'm not dropping any local minimizers from the constrained problem. So it makes sense for me to try to solve the unconstrained problem. And the way I'm going to do that is I'm going to apply cubic-regularized Newton to solve it. And we'll get to the reasons why cubic-regularized Newton is a fitting algorithm in this setting. It has good properties which make it a suitable algorithm to apply to this non-convex problem. So the general spirit, though, of cubic-regularized Newton Rn, we'll discuss that first before we talk about the matrix setting. So some classical assumptions that you might make on a function. It's non-convex when you're doing theory. convergence theory for an algorithm is you'll probably assume the function is gradient Lipschitz, which you can weaken that to say I want my function to be locally Lipschitz, which is a very light assumption, all things considered. But if I have this assumption, one classical result I can get out of it is this sort of like gradient Lipschitz inequality. So I generate a quadratic upper bound if I allow the sort of gradient Lipschitz condition, which bounds the growth of my gradient. And because of this, and just optimization in general, what I'm going to do to solve my original optimization problem is probably solve a set of smaller optimization problems. So locally, say in my iterate xk in my algorithm, instead of minimizing my function entirely, I'm going to minimize a surrogate. I'm going to minimize a function that approximates the value of my function. So if I have a gradient Lipschitz condition, I can minimize, say, this quadratic upper bound of my function at my previous iterate and show that that will present a decrease. And if you minimize this quadratic upper bound on the right, what you'll see is you just get gradient descent with a fixed step size equal to the 1 over the Lipschitz constant. So cubic regularized Newton, the spirit is well, let's say I have a gradient Lipschitz condition, but not a gradient Lipschitz, a Hessian Lipschitz condition. So now I'm going to say, well, the second derivative of my function also has to be bounded in a certain way. And from this, you can derive a cubic upper bound. And the spirit behind cubic regularized Newton is to say, I'm going to minimize the cubic approximation of my function at each iteration. And Nesterov and Polyak in 2006 had a paper where they essentially showed global convergence guarantees for this type of approach. And there was kind of a new thing in terms of like giving good worst case conditions for these second order methods that are protected in a way. And by protected, I mean global convergence results. So for cubic regularized Newton, what we're going to do at every step is solve a model that looks like this, where I have my previous iterate xk, and now I'm going to solve this cubic upper bound, minimize this subproblem every step. And mk is a positive parameter that I get to play with. I can be adaptive. And in this sense, I really just need a sort of like local Hessian condition for my function. And the nice thing is that though this is a non-convex problem, we can show global minimums exist. There's plenty of results that show, oh yes, this has a solution and it has an easy description from a set of equations. And if I solve these equations, I'm guaranteed that's a global minimizer for my non-convex problem, which again is a nice thing to have. Because if we say, like, let's do a quartic problem, let's do a fifth power approximation, it's going to be harder to say, do I actually have a solution to this subproblem? And the last thing you want to do is try to have a subproblem that's just as hard to solve as the original problem. And you can prove under weak assumptions that if I solve this iteratively, I'm going to get a decrease in my function value. And this will guide us to actually obtaining a solution. So some standard sort of assumptions you might make for this type of model. If I'm working in Rn, it's unconstrained, Lipschitz Hessian, I want my function to be lower bounded, and I'm seeking second order epsilon stationary points. So what that means is the norm of my gradients is less than epsilon, and I'm asking for the lowest eigenvalue to be greater than negative epsilon. So if epsilon goes to 0, I'm going to have my second order necessary conditions for my problem. So this is a relaxed way of returning a solution. The general algorithm, as it looks, is, as I said, you sort of have this choice of m as you go. You're going to ask for a sufficient decrease, and this is a model that's a cubic model, but it's going to be strictly less than the actual value of my function at the previous iterate xk. But this is the problem we have to solve step after step. And in Nesterov and Polyak's paper from 2006, they showed a couple of results, but the two big results are here, is that I'm going to globally converge to a second order epsilon stationary point under appropriate assumptions. And really the only extra assumption you need is that the level sets are going to be bounded eventually when you hit an iterate. So you just can't have a sequence running off to infinity and it keeps decreasing the value of your function. So then you really can't say minimize this function 6 is probably not going to be well defined. Take the infimum of that, and then that could be well defined. Second thing is locally, you're going to get quadratic convergence if you're near a non-degenerate stationary point, which is what you want. Like I'm sublinear globally, but locally I'm going to race to a second order solution. And these are the two properties you'd really like, because this sort of links together the benefits of a higher order method, but also with a gradient approach. Is like a gradient approach, you can do things to guarantee global optimality. It's much safer. And by global optimality, like I can initialize my algorithm anywhere and it's going to go to a solution. If I just use pure Newton, say, and I didn't have safety measures in place, I can't ensure global convergence. I could give you a point to start the algorithm and it's not going to converge, which is going to be a problem. So I want to move over now to the matrix optimization setting. And for that, I need a few definitions. So I have an operator norm, and this is taking the place of, say, the 2 norm for matrices in the Rn case. And I'm going to use that to define a Lipschitz-Hessian condition in my matrix setting. So very much analogous to what I had before. And because of this, we can get the same sort of upper bounds as we had in Rn, where now I can still get a cubic upper bound in my matrix setting. And if you go to a text like, say, Absil's matrix optimization text, you can see that an inequality like 8 and more general inequalities like 8 will show up as long as you assume high enough orders of these Lipschitz conditions. Before the matrix setting, we're still going to assume very similar things, but now I'm going to be dealing with V being a d-dimensional subspace of Rn by n. I still need it to be 2 times continuously differentiable. I still want it to be lower bounded. And we're still going to be working for second order epsilon stationary points. So the norm needs to be less than epsilon, and I want my directional derivative, my second order directional derivative, to be bounded properly below. So as epsilon goes to 0, this comes out to be the second order necessary conditions for our problem. The algorithm in the matrix setting is very much the same. It doesn't look any different. And in our paper, we present a different type of convergence analysis that's very much just extending what Nesterov and Polyak did, without running into some different terminology that's used in other papers. Because this is very close to sort of like a matrix manifold setting, which you might need to introduce different terminology. And the proof that we present is simpler than some of the others that you could have. But we get the same sort of convergence results in the matrix setting as you'd have in the setting in Rn. You still get global convergence at the same rate, and you still get local quadratic convergence as long as you're away from a non-degenerate stationary point. And by non-degenerate, we essentially mean at x star, the second order derivative in all possible directions is going to be strictly positive. And this would be like saying the smallest eigenvalue for my function, if I'm going from Rn into R, has to be positive. So the Hessian has to be positive definite at that point. This is cubic-regularized Newton. And this is what we're going to apply to solve our model. But now I want to get into the sort of numerical experiments in the last 20 minutes or so. So what we're going to look at is an application for robust covariance matrix estimation. So this was actually the impetus for this study to begin with. We were really asking for the model I'm going to show on the next slide, because I can rewrite 10 as an optimization model. But really asking, can we apply higher order methods to solve this problem efficiently and say faster than other ways that exist? So that was sort of like the spirit behind what we did before we came across this like broader class of models that we could solve. But the Tyler estimator is all about trying to develop and find a robust covariance matrix for a centered data set. And if you solve equation 10, that is the sort of estimate that you're going to get. Plenty of results show the robustness of this estimate. Now, really what 10 is getting you is a shape matrix. And the shape matrix will be the same as the covariance matrix up to scaling, assuming it exists. But if it doesn't exist, you'll still be able to have a solution. So a common assumption people might make on 10 is that because I can scale my matrix R by any positive value, it doesn't change the equation any. Often people will add a trace constraint. And you can show that solving equation 10 is very much the same as solving optimization problem 11. And you can see the relationship between these two by computing the derivative of 11 with respect to R and seeing that the first order optimality conditions of 11 basically give you out 10 equivalently. So this is the model that we were like, we'd like to solve this. We'd like to apply higher order methods to it. So what people currently do to solve 11 is they apply a fixed point approach to it. And you can prove linear convergence under different data assumptions. And it's very efficient because this is the update that you're doing. So you're really only having to incur basically matrix vector multiplications and a sum. So you can still get challenging problems, but it can be very efficiently done. And you will scale it. And this, what's in blue, would enforce, say, a trace constraint for your iterates. Now, what we wanted to do when we saw this model and we've seen our algorithm that we have, we started asking questions of fairness. And the question would be is, well, can you have also a fair as well as a robust covariance matrix? And the setting is similar, but it's slightly different than the Tyler M estimator model. The setting is this. Let's say I have a data set, and that data set can be broken up into many subgroups. Say I have R, they're independent. They could vary in size. They could come from different distributions. But I need to get a covariance matrix that kind of represents the group as a whole. But I'd like to kind of be fair to the different subgroups. It might just so happen one of them has fewer samples, but that's no fault of theirs. And we'd like the covariance matrix that's kind of to represent the whole, say, not be swamped by a subgroup that has more data, for example. So this is sort of, we'd like to have a fair covariance matrix that's robust for the data set. So in order to build this, we leverage the Tyler M estimator model. So I needed to define something, say, a TME error for the J subgroup. So the function fj that I have is the objective function that you see in problem 11. Okay. So the TME error is going to be the difference between the best value you could obtain for this problem and the solution you get from the TME model. So this is the objective function from the TME model. If you write it as an optimization problem, fj star is giving you the optimal value you could obtain. And I didn't mention it before, but on model 11, it's geodesically convex. And as long as the data is appropriately given to us, we can solve it. We can solve it to global optimality. There's a unique solution. So I know fj star is going to exist. So my TME errors, these E sub j's, are going to be strictly non-negative. And they are measuring, in a sense, how far R is away from being the best covariance matrix for this data set subgroup as measured by the TME error. Now, what I'd like to have a perfectly fair covariance matrix for my R different subgroups. And I can use these TME errors to define what I mean by perfectly fair. And what I mean by perfectly fair is that all of these TME errors, I'd like them to be the same. So essentially that's saying all of the data sets are equally far away from their best covariance matrix in one sense of measuring that. I'm not measuring this in terms of like how far are you in terms of like in the vector space of symmetric matrices, how far are you away from your best? But how far are you away from a matrix that minimizes your TME error? You're as close to the best solution you should get for the TME model. And with the spirit of this perfectly fair covariance matrix, I'm going to then set up a fair TME model. So we'll take this slow. I have two constants, fixed constants, mu1 and mu2. And I have two major terms in model 13. This first term is trying to minimize the individual TME errors for my model. So this one, in some sense, is trying to give individual fitness for the covariance matrix for the individual subgroups. If, say, E1 is small, say close to 0, that means the first subgroup of the data set has a covariance matrix that's really close to the best it could have. The second term, though, is trying to work towards fairness, because if all of the TME errors were the same, this term would be 0, and that would correspond to them being perfectly fair. So you can see this sort of like give and take of mu1 and mu2. If mu1 is very, very large, it dominates mu2 in terms of their ratio, you're really saying, I just want to get the TME errors as small as possible. I don't care if they're the same. Now, if mu1 is very small and mu2 is relatively large, you're saying, I only care about fairness. And if the individual TME errors are very large, I don't really care. I just want you all to equally be far away from your best, but you're all the same. So there's sort of an in-between where you're like having good TME errors, which says you're close to the TME model's estimator, and fairness would correspond to the second term being small. So you sort of have a fair covariance matrix amongst your data set. So now I'd want to solve 15 using the proposed procedure that we've discussed. Now, one way you could do this is to just say, I'm working over the set of positive definite matrices. I'm just going to use the matrix exponential and I'm going to use that as a change of variable in 15. And you can do that. And in some cases, it'll work fine. The danger that you have with using the matrix exponential is that in your numerical experiments, overflow is rather easy. So you could quickly get elements of your matrix that get rather large. And if you need to do any sort of operations, say like solving a linear system, this can start to have numerical issues where it becomes unstable. Another way to deal with this problem 15 and remodel it and still use our procedure is to first apply a change of variable, replace R with R inverse, and then apply the matrix function R squared. And if you do that, you can remodel 15 in the form of 16. And the reason we do this change of variable is that when you do the change of variable, this term, and I've slightly changed the way my functions E look, so it's E hat now. When I do that change of variable, this term becomes a barrier function. So now if R had determinant 0, you have infinite penalty here. And I'm minimizing this function, so I'm not going to allow R to become, say, determinant equal to 0. So you could rephrase it as a problem over the set of positive semi-definite matrices, and then I apply the matrix function R squared. So we solved 16 in our numerical experiments for both simulated data and real data sets. So we use that as well to then obtain a solution to the original problem. So if I solve what I have in 18 and I get R star as a solution, I can get back a solution to my original fair model through my variable transformation and through my matrix function. And that's really what we're going for, is I'm solving 18 in order to get a solution to my original model, or a good solution, a local solution. So we need to measure fairness, and then one way we can measure fairness, and in our numerical experiments, we give back two measures. We give back the TME errors, and we give back something called a fairness value. And the fairness value is essentially the maximum absolute difference between the TME errors. So we're going to say you're only as fair as how far apart the best and the worst TME errors are in your subgroups. So if you had, say, 5 subgroups and 3 of them have the same TME errors, but one has a very small one on the at one extreme and another one has very large on the other extreme, well, your fairness value is not going to be that good. And the naming convention might not be the best. Right now, if the fairness value is 0, that means you're as fair as you can possibly be. So bear with me with that sort of naming convention. It's in print right now, so at least it's sent off. I'll have to change it maybe at the first round of reviews and make it the unfairness value. You want unfairness to be 0. So we dealt with simulated data and real data experiments. In the simulated data, I had, say, 4 centered elliptical subgroups, and I drew them all from R30. So not a very large dimensional problem. And they were all generated in the following fashion, where I had a positive definite matrix SP, and I have uniformly drawn random variables from the sphere in R30. And I'm just doing this matrix multiplication to generate points X that are in my data set. And I have subgroups that contain 50, 75, 100, 200 data points. So they have same type of distribution, but they have different matrices that are generating the data, and there's different number of points. And we solve our model, and then we return a solution to our fair TME model. For comparison, we compare our fair TME model to just standard TME. And for standard TME, you just lump all the data together as an aggregate and say, I'm not going to notice any distinguishing features between your individual subgroups. I'm just going to treat it as one thing, throw it all in one big bucket, and solve the model as I would before. And when you do that, this is the sort of results that you can obtain. So on the far left, I have different choices for parameter values, mu1 and mu2. So remember, mu1 being large means I want the TME errors to be smaller. Mu2 being large means I want to advocate for fairness. So if I look at the most strict setting for fairness, mu2 being 10, mu1 being 1 in this column, we'll see the fair TME model gives out the best fairness value. It's really close to 0. If it's 0, that means we've obtained a perfectly fair covariance matrix. If I just apply TME, well, the fairness value is rather large. It's many, many factors larger than the fair TME model. But the thing to note is that this data set had 200 data points. This subgroup had 50 data points. The individual TME error for the subgroup that had a few points is much worse than the TME error for the data set that had the most points. Whereas for the fair TME model, there's not so much this discrepancy. So the one that had the most, 81.2, the one that had the least, 81.2. So they're very close. And this is sort of the spirit of trying to advocate for fairness in this model. Besides doing simulated data, we also worked with some real data sets. But before that, I want to look at this picture a little bit. And we might not get too much time for the real data set, but I do want to talk about this. So these are various convergence plots for applying cubic regularized Newton to the fair TME model. Again, we choose to apply cubic regularized Newton. You don't have to. You can apply other algorithms. But this kind of showcases the reason why a higher order method might be beneficial, especially if your model is highly non-convex, which is the case for this model. And the amount of convexity in this model, or what term is going to bear the most weight in the model, depends on the parameter setting. So the parameter setting in the bottom right is by far the most difficult of these problems to solve, because mu2 is weighted greater than mu1. Mu2 has the difference of all the TME errors and that distance squared. That term is highly non-convex. So the greater you put your focus on that term in the model, the harder this problem becomes to solve. And that's what plays out when we apply these first order methods. So what is in red is a gradient descent approach. What is in blue is a conjugate gradient descent approach from a good software package MANOP that it works on manifold matrix optimization problems. And even in terms of like computational time, if you look at the very strict setting, the first order methods are slow enough that the higher order method not only does better in terms of iteration complexity, but also in computational complexity. It can be better. So we also worked with some real data as well. We worked on 3 different real data sets, and all these data sets came from the FAIR PCA literature. So there's not too much in terms of like fair data science models that exist right now. They're growing in terms of number, but the FAIR PCA is probably like has the most. So each of our data sets were ones that had been utilized in work that has been recently done in FAIR PCA. And we applied a processing of our data in the same sort of way that was done in this paper from the FAIR PCA literature. So we'll remove categorical features. That was kind of for us because we're dealing with continuous problems. You don't need to remove the categorical features, but we decided to do that. We'll center them. We'll center our subgroups by subtracting the mean, and then we will sort of normalize so it's unit variance. So this is good actually just for the stability of the algorithms. And also because in these sort of data sets, some of the different things you're measuring could have vastly different sizes in units. So this normalization is a good practice. For the TME model, we did the same type of centering and processing of the data, but we just did it all together. So for the FAIR TME model, you process each of the subgroups separately. For the TME model, looking at it, just brought all the data together, did the same sort of processing steps. And I'll look at one example of these. I'll look at the credit example. Maybe I'm just thinking about wine. Let's just do the credit example. So I have 8 different categories. And they're all broken up through sex, marital status, and education. And this is coming from default credit card data from Taiwan for 30,000 individuals. So a fairly large data set, though the number of factors that are being tracked for each individual is fairly small. So 19 for us once we did the processing. So the way I'm labeling this is so like male, married, high education just means it's a married man. He has at least a college degree. And the data set is tracking, say, how much credit you have. How have you like paid your payments? Have you defaulted on a payment? Have you lagged behind? How much is on your bill statement? How much did you pay on that bill statement? So these are the sorts of things that are being tracked. And the idea of a robust and fair covariance matrix here is that, well, if I'm going to use a covariance matrix, and it's kind of going to represent my data set, well, it's got to represent each of these 8 groups to some extent. And our model would help to do that. How to quantify that yet, we're still thinking about because it's a relatively new model. That's one of the questions to ponder in the days to come. But for this individual example, these are some of the results that we can see. So I have more groups here. But in the most stringent case for fairness, the fair TME model still outperforms the TME model in terms of the fair value that it gives. So by a factor of about 16. But the thing to note is that the data set that had the fewest number of points, male, single, low education, about 980, just say 1,000. A female, single, high ed had about 8,000. So about a factor of 8 difference in the number of data points. The TME model on its own, the lowest value it gave for TME errors was from the one that had 8,000 data points, the greatest number. The worst TME error that it gave was for the one that only had about 1,000 data points. The fair TME model, though, doesn't make that sort of distinction between the two. Male, single, low education, 1.5. Female, single, high education, 1.45. So there's still a difference there, but the difference is much smaller, whereas the discrepancy between the two was much larger if I don't actually treat these different subgroups as sort of what they are, a different subgroup of the entire data set. So I'll leave you with a few thoughts on what we're going to try to do next. One thing is like, does the fair TME model relate to fair PCA in some way? So I have a covariance matrix. I claim it's robust and I claim it's fair. Well, can I use that, say the top eigenvectors of my fair covariance matrix, to do something like fair PCA? And I project down on a lower dimension. And can those two relate? Do they differ? Is there some connection between the two? We don't really know, as the model is something we've recently produced. The second thing is, and this is one that I'm focused on right now pretty heavily, is what different types of spectral constraints can we handle? So I only am handling this model's interval constraints on my eigenvalues. And I really have lots of different types of constraints I want to deal with. So one in particular that I'm working on is, how do I deal with, say, linear inequality constraints? So if I have a matrix A and I give you my ordered vector of the eigenvalues, can I solve a problem where the constraint is, say, the matrix A times my vector of eigenvalues is less than some vector B, less than or equal to some vector B? That could capture lots of different things, different types of trace constraints, different types of summings of your eigenvalues. And it could have some applications, but currently the literature seems to be very non-existent with these more general types of constraints on eigenvalues. So these are a couple of things that we're thinking about right now. I need to have a slide that acknowledges those who pay us to do our work, so I don't get in trouble. But besides that, I just want to thank you for your time and open up to any questions that you might have. Right on time, as in, like I did it. I don't left no time for questions, or I left time for questions.
Exactly the time for questions.
Fantastic. I was going for 50 minutes. I guess I did a good job.
Okay, yeah. Thank you, Casey. People at home, you can type your questions in the questions and answer box. Any questions in the audience?
I have a very kind of naive question about the fair Tyler and estimator.
Yes.
So, do you get have you considered something much simpler where you just kind of weight the points by the size of their group? So a small group would have larger weight, and then you do Tyler's M estimator, but a weighted version of it.
We hadn't thought about that. And I'll say one of the reasons I didn't think about that is because I wanted to get something for model 8, say, that was sufficiently non-convex to motivate the idea of using cubic regularized Newton. So like every algorithm has its place. And if you're trying to apply a higher order method where a first order method is perfectly useful, quit trying to put, round objects in square holes. So if I just decide to do a weighted version, a first order approach, like the fixed point approach that they have, is probably perfectly good. What I would need to do is I need to do a comparison. I say a weighted model that is much simpler computationally to solve compared to the fair TME model, and see which one of them comes out. That'd be a good thing to do, especially if we can show that this fair TME model has strong connections to, say, like fair PCA. And then at that point in time, I would much rather solve a simpler version of the fair TME model and have good connections to, say, like fair PCA and fairness. But we'll have to talk more about that. But that is a good idea, just to see if a weighted approach for, just based on the number of data points that each subgroup has, if that would be sufficient.
Earlier on, when you had that little example of minimizing x squared and then
Yes.
the constraints of x squared.
Yep.
So you take them into a convex problem and turn it into a non-convex application.
Yes. Yes.
Is that a general thing that method, or is there any thought to trying to preserve convexity that's there?
So that, I mean, in the sense of the original TME model, like it's geodesically convex. So it would fail to be convex in a sort of traditional way of thinking of convexity. If the problem that you have originally is already non-convex, then doing this sort of change of variable, yeah, it's a fine thing. But if you have a convex problem and it is constrained, and the constraint's not convex, then it's an interesting question to have, like, what would be better? Would I rather remove my constraint and be non-convex, or would I rather keep the constraint and maintain convexity? And what I have in red, like doing what's in blue, would be very, very dumb, because I have a convex constraint set and I have a convex function. So in our case, for the general broad class of models that I suggest at the beginning, I'm in a sense already assuming that F's non-convex. So I'm just taking something that's non-convex and maybe making it worse off, which is another reason why to apply something like cubic regularized Newton, is to be able to escape, say, bad stationary points.
Here's not so bad.
No, here's not bad at all. Yeah. No.
They're both good.
Yeah.
And at the same level.
Yeah.
Is there any theory about that in general? Is it a complex problem? Constraints in place becomes non-convex. Is it nicer than in general?
That I don't know. I would need to actually look in the literature more for that. But this is a good question, because you are increasing the number of minimizers, but that could be good because now I have the better chance of initializing somewhere and getting it. So yeah. But I don't know if that's in the literature anywhere. It's not like a normal thing people will do. Most of the time, people have a convex function and convex constraint. They say, I'm happy with that. So I know this question in the back.
Yeah, if you could go back to the slide where you're looking at the credit data and you were analyzing.
Credit data, okay.
You were analyzing the fairness ratings.
Yep. Eventually I'll get there. And we've arrived.
Okay. So I think you may have answered this question already, but I just wanted to clarify.
Okay.
So in the just standard TME model, you had noted that there was at least somewhat significant gap between the data set that had a lot of data points and one that had considerably smaller.
Yep.
And in the fair TME model, you noticed that the model, the result, basically the ratings came out roughly equivalent. So is it a fair way to say that the fair TME model kind of controls for the different the differences in like sizing of data sets, that kind of like what one of the big goals of it is?
Yeah, in one sense it does that, because in the model, I'm not really caring about the size of the data set too much, because in the end, the way I'm measuring how close you are is just how close you are to the optimal solution of your own TME model, which already takes into account the number of data points that's present. So in some sense, it doesn't actually look at the amount of data. So you could say, in one sense, the fair TME model might go too far in the other direction. It says the amount of data that you have, I don't really care. So if there was one data set that had like 5 points, and another one had 5,000, the fair TME model is probably going to say, I don't really care too much that there's that big of a difference. When in reality, it's like you need to pick whether or not the tool you're using is good for the task at hand. So there are times when few number of data points, well, I don't really need to consider those because this is like very, 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 very small in my application. But yes, the fair TME model in some sense can eliminate, not quite eliminate, reduces the amount of impact that a discrepancy in the amount of data that you have in your subgroups, how much that is going to impact the final result.
So is there like a mathematical way of like determining when you would want to weigh data set size heavily as opposed to not, or is it more like a judgment call based on the context of the problem? I
mean, just in general, I'd say that would probably be a judgment call depending on the application that you're dealing with. And for our own model, I don't yet have sort of mathematical results that say, this is what's going to happen if you choose mu1 and mu2 to be these values for this type of data set. Because I think you'd have to make a few assumptions. One is like, you need to be more precise on the type of data that you're dealing with, because this model very much does depend on the types of data sets that you have and say the distributional assumptions that you're making on them.
So quick thought on Jim's question.
Yes.
If the map is monotonic or the map is convex or map
But you can use the e to the x in this example.
Yes, e to the x is a good example where, because it's 1-to-1, you're not really changing too much. And it's also monotone. And there are results about that kind of show that if I do this sort of like take my constrained problem and then make it unconstrained, as long as the function that you have in the composition has the appropriate assumptions, you're essentially going to have, say, a one-to-one correspondence to see like second order stationary points, which if your function is already non-convex, like you're very happy with that. And yes, monotone is a traditional sort of thing to assume to try to get those types of results.
And another quick question.
Yes.
Is when you in the proof, you assume that the first derivative, the second derivative are bounded. But I wonder, so I also assuming that your x is bounded, because if I'm thinking of a very simple f, say x to the power of 3,
Mhm.
then it won't satisfy this condition.
Yeah.
It's very,
So the I mentioned it at one point in time, but I didn't probably say it enough. So right here, the level sets of the iterates become bounded eventually, and this handles the problem that you're dealing with. So in that case, e to the x, the level set would not be bounded. So level set f of x being less than f of x naught. In that case, the level sets would never be bounded. So you wouldn't be able to say global convergence occurs. You would need to add an additional assumption to say to ensure that. But yeah.
E to the x and if you solve it in multiplicity,
Mhm.
but you have an issue of possession.
Yes. So that one comes down to computation, and that comes down to also the objective function that you're originally dealing with. So, and it's always the sort of give and take when you apply a higher order method. If you want to apply a higher order method, have the benefits of second order differentiability, use the second order information, you have to compute it. And in the TME example, the problem is sufficiently complicated enough that when you add the matrix exponential, it just is a computational burden. So in terms of the like numerical results and the many examples that I've seen, if I do e to the x, the rate of convergence is much nicer and much cleaner. The landscape is cleaner than say if you do x squared. You proliferate local minimizers that might just be first order, might not be second order, and make the landscape much more difficult to deal with, where a matrix exponential gives you a cleaner landscape. Or at least it doesn't gum up the landscape that might already be complicated.
Might be harder.
But it'd be harder to compute computationally.
Yeah, let me also ask you, so you had a claim before that second order epsilon stationarity kind of sometimes guarantees the
Yes.
global optimality.
Mhm.
And let's accept it. So if you
I can give you a reference later. So.
right, you mentioned it before.
Yeah.
But if you want to be more concrete, if you
Mhm.
talk about the fair TME model, do you think you may have a chance
To be able to show that,
to do something there? Yeah.
I think it might be possible. It might be true. In the sense of depending on the data set that you have, that'll be the driver for that is under what data assumptions would you need to have in order to have second order stationality ensure global optimality. But I've had, different algorithms run on the same problem and they're converging to the same objective value. And that, if I'm using different algorithms, and they're definitely generating different iterates, if they give me the same result, I'm like, well, it's possible that they're both converging to say a global minimizer, or they're both being initialized in some well that they can't escape. It wouldn't surprise me if you can do that. One is because you're starting from TME, which is geodesically convex. It does have a unique minimizer. And we're moving away from it in the fair TME model, but we're not moving so far away from it that it might not be possible. It would be a good result to be able to prove for the sake of the model.
Any other questions? Okay, thank you very much.
Thank you, guys. Thank you for everyone that's on the video call. So have a great rest of your day.
Thank you, Casey.